to configure a CloudFront fronted registry, we couldn't really find a lot of content that wanted to do this. We went rogue, even without AI. Crazy to think that we did this without AI. I'm lying, of course. Some interesting optimizations that we can do cost-wise. Performance-wise, we're not gonna get any better than this.
No, it's actually almost 100% faster than pulling from GHCR directly, according to what we saw minutes ago. So,
and it's 1,000 times more expensive.
Yeah.
Because GHCR was free. So we're trying to get a registry to work through CloudFront. So CloudFront is actually fronting a registry. The registry which is fronting, it's the ghcr.io. We can see a pull-through registry. We can see that in the description. So that's what we're trying to achieve. Now, why is this important? Why do we need CloudFront? Why not just GHCR, or why not something else?
GHCR is extremely generous. They have a free tier, I guess, of like you just pushing a public image and so many people downloading it, and it works completely fine. You can go so far. Like, we've been using GHCR for 3-4 years, maybe. Like, the first time that you set it up initially, like, I think it's been a while.
So you can see when that was published and how long it's been.
There we go. Yeah.
And where we are.
Yeah. So we have 792 million pulls since November 7th, 2022, which I think the most interesting thing is that the majority of these pulls have happened in the past like year and a half, or maybe even less. We were using GHCR.io to publish the engine, the image of the Dagger engine. Now, the special thing that we do is we want a custom domain. We don't want people to do like ghcr.io/dagger/engine. You can do if you want to, but we want to give an interface that's slightly better. And for us, that means that you do engine and then the engine version. There's a bunch of ways that you could solve this. There's a few reasons actually why we want to give this. It's not just a better experience, it's also to capture just a little bit of data that helps us understand the growth that the Dagger project itself is having. You could just look at this, but this doesn't tell you much about like a daily breakdown. We don't see much.
Exactly. So I think this was like something that's been missing, having a bit more insight, having a way to maybe switch away from GHCR or add more registries in a way that is not disruptive to users. That was like one of the first things. Like, whatever backs registry Dagger.io, we will make it easy for us to change it in the future. We know we will want to, because one registry will not be big enough. And I think we're approaching to that point where GHCR itself, we're sending so many requests that there are moments when it struggles. Like we're seeing like 429s, too many requests, slow down again. They're very generous, and this is very, very good as a service. But the truth is that we are starting to see the limits, at least for us, of the service.
And the thing is that when those errors happen, there's nothing we can do. It's just, and it's kind of upsetting to tell a user like, hey, can you try again? And that's it. Like, it's just a matter of, okay, it's a fluke. It's something happened and we don't know what, so try again. The setup that we had to get that visibility into what's happening with the image, like not necessarily who's pulling it, but how many users are pulling it, and a little bit more information on the activity that this image is seeing. The interesting thing about this project is it's actually quite easy to see exactly what's doing. You can go to this file, redirect.go. Registry-redirect is basically a simple Go service that acts as a front to another registry. It simply allows you to put a URL in front of like GHCR, GCR, like whatever registry you want. Actually, it only supports those two, now that I think of it, only GCR and GHCR. I don't think it supports all. And it doesn't do much more than that. Like, it only handles a few requests that allow you to, for example, configure something like this. The special thing that this has is that you can see that it's not only a custom domain, but it's also a different image, because when you go to GHCR, right, you do Dagger engine, but here we're just doing engine. So clearly the registry redirect has some knowledge on what the repository is, and it just knows to pull you through to the right place, right? And it's actually a simple service. We're not going to look at the code here, but you can see that it's a good way of understanding also like what Docker pull actually does, like what it needs, not what it does. you're going to see that it needs just a few endpoints. Like you need a V2, you need a token, and then a few other things within V2. And with that, you're going to be almost done. It's going to capture the majority of the requests that you need in order to handle it. So
Very
this
nice.
is what we're using deployed in Fly on this instance called Dagger Registry 2023 0123. And the interesting thing, the nice thing for us is that within registry redirect, we can do logs. We can just add our own logs that log some information on the request that's coming, like which manifest is being requested, like those kinds of things. So we can have some analytics on how many users are still using 0160, right? And answer those kinds of questions. So we log that, and we have another setup, which is vector, and using some internal like workings of Fly, we can get the logs of the Dagger registry in this instance, in this vector instance, and then vector just pushes them to the destinations that we care about. If you don't know what vector is, it's like a component that for me it was a new component. I wasn't aware of it before Dagger, and it's basically like a place that centralizes different inputs and takes them to different outputs. You can think of it like Kafka Connect, but more lightweight, and specifically for observability, logs, and that kind of information. You can actually do a lot more than that because it's just HTTP under the cover. But yeah, you can just ingest logs, transform them, do a bunch of stuff, and then send them to the place that you wanted to send them or discard them.
It reminds me to the old Logstash stack from Elasticsearch.
Yeah.
But for the modern world, yeah.
I'm pretty sure it's based on that. I mean, it hasn't been around that long. I mean, it's been some number of years. But I think the focus on lightweightness, like how lightweight it is. It's using very little memory because it's Rust-based, so it's very efficient in that way.
It's literally just a binary, right? Yeah.
Exactly. Single binary. The expectation is, as a sidecar, it's a good candidate for that because it's super, super efficient. So run as many as you need of these. Lightweight, super cheap, and fairly easy to configure. Good documentation as well, so we had a good experience with it.
Yeah, there's also been some other ones in the cloud native ecosystem, like FluentBit, Fluent something. Yeah, it's been a while since I last saw it.
Yeah, I remember that one. Yeah, FluentBit. It's been, I think it's still used in a bunch of places.
Yeah, probably.
It's nice and reliable. So because you mentioned about the requests, Matias, and requests that Docker makes, Marcos was showing us something really interesting the other day.
So when we started setting up all this, and Matias is going to show it afterwards with CloudFront, some things weren't quite working out of the box, right? Because you need to intercept some requests, and then you need to decide what to cache and what not to cache. So it was important for us to understand the traffic, the HTTP traffic or HTTPS traffic that is flowing from your machine to the endpoint that you're actually hitting. In our case, it is CloudFront. Yeah. So for that, you have two options. One is like what generally people do is like you add like a man-in-the-middle proxy, right? So basically you install a piece of software in your machine that basically has some TLS certificates that basically talks to the underlying endpoint that you want to communicate to, and then you set up some proxies that use this proxy server that you created, so you can actually intercept the traffic. And then the second option is to do what I did, which is basically, there's a project that I found some time ago that is called eCapture. And this is something, it's funny because this is something that I was actually looking forward to do back in the days, which is basically, I had the same question that regarding like a filtering or inspecting the traffic that I just explained a few years ago. And then a few years ago, also eBPF, which is basically a technology that only works in Linux so far, that allows you to like add specific instrumentation into the Linux stack, right? So you can basically write very small, non-Turing complete programs that allows you to like basically perform like very specific tasks in the kernel. And generally, these kind of programs are mostly used for either observability or network handling, but you can actually do a lot more things. But usually the most important use cases for now are those. There's an observability project that I believe Gerhard likes a lot, which is called Parka, is it?
Parka.dev, Parka.dev. It's been a while,
Yeah, that also like gives you like Go observability using the same technology. But yeah, in any case, what this does is like it basically allows you to capture SSL and TLS traffic in plain text without a certificate or without setting up a man-in-the-middle proxy, as I explained before. And as you can see, supported on Linux, Android, AMD, and ARM64. So the gist of it is that you download this binary. The documentation is quite extensive. It's becoming quite a popular project. So you download this eCapture binary, and then what you can do is like, you need to run it as root, of course, because in order to like call the eBPF syscalls, you need like elevated privileges. And then, as you can see, you have like different flags. You can either instrument not only SSL, but also you can instrument like bash commands, GNU TLS, GNU TLS. You can instrument Go TLS, MySQL, Postgres, like standard TLS, and so on. Since we are doing a Docker pull, what happens when you do a Docker pull is that the CLI, the Docker CLI, communicates with the Docker engine, right? And the Docker engine is the one that actually pulls the image for you. So in this case, we want to instrument the Docker engine binary. And because it's a Go program, you need to use the Go TLS feature of eCapture. So you need to do eCapture, Go TLS, and then you need to supply, I think it's ELF binary, ELF file. You need to supply an ELF path, which is ELF is basically the standard of the file definition binary format. So ELF path, and then user pin docker-d. In case you didn't see it because I was typing a bit fast, I basically supplied the docker-d binary, and this is gonna basically run the eBPF program, and it's gonna basically hook to the underlying syscalls that Golang does. And the reason why this is different than standard TLS is because Go has its own. When you build Go with it's a single as a statically linked binary, it is not going to use the libc TLS implementation. It's not going to use like a libTLS. It's going to use its own SSL implementation. That's why. And it's going to basically do its own syscalls, its own like basically handling of all that part of the stack. So that's why you need to run it in this mode only for statically compiled binaries, which is the case of Dagger.
And Docker is already running, right? So Docker, you didn't have to change anything about it. That's already running. All that you did is basically you started eBPF trace, was it? Trace?
eCapture.
eCapture. You started eCapture. And you just basically attached it to something that's already running.
Exactly.
ELF path, and now it's introspecting all the HTTP calls.
Exactly.
HTTP
so now,
calls.
It's going to introspect all TLS calls. I don't know if it's going to introspect like non-TLS. I haven't tried, but anyways.
All TLS calls. Cool.
Yeah, so now you can do a Docker pull, and we are going to pull Alpine, bloop. And as you can see on the right, it's already showing things. So we can start from scratch. So this is when the program started. So now you can see that the first thing that the client does is basically try to communicate to this endpoint. Right. And then it's going to receive. And then you get a realm, right? And then you're going to get an authorized, right?
You have to get the token before you can.
You need to get a token. Here you can see that I have the authorization header, right? I think it got this response because I'm already authenticated, so it probably used like a refresh token or something. But then here you can see the response. This is like a request. Here you can see the request header to request the token. You can see the response, right?
Yes.
Okay, application JSON, whatever, and then you can see the response body, right? This is the new token that the service is sending me. And this is where the important part comes, which is what Matias was explaining, and he's going to go back into this in a minute, which is, okay, now I do a head request towards this path, right? Like V2, library, Alpine, manifest latest against registry1 Docker.io. And this is all the request headers that I sent, right? This is the token. This is all the accept headers that the registry basically validates in order for the manifest to be on the same specification that the one that I'm requesting. And then what you get back from this, it's an okay, right? Yeah, I didn't get anything else because I already have the image locally, right? So it didn't have to pull the image. If I'm about to, let me clear this out.
What happens if you pull a registry Dagger.io, if you pull an image that you don't have? I'm very curious to see those requests. What do we see? What endpoints do we talk to?
let's pull V18.1.
Oh wow, that's a lot of data.
I'm getting the binary data of this because it's like basically pulling the layers. Yeah.
Okay.
But
so that's going to be a lot of data.
So here's the beginning. Again, I'm doing as you can see, I'm doing the token handshaking part again, right? Because it's a different endpoint. Here, I got like a gzipped response. So in this case, it's funny when you talk to GHCR directly, to Docker Hub, you get this in like a plain text. But in this case, it's basically compressed because it's like content encoded in gzip.
Yes.
So you don't get it. So it's going to be lighter, right? Because it's like compressed. Now I do like the same head request that we saw before for Alpine. I do it for the manifest that I've just requested, right? And in this case, I get the manifest, as you can see here. This is the manifest of the image, right? And as you can see, this image has the, because I'm already in an AMD 64 machine, this is going to result to the AMD 64 manifest. And as you can see, I get all the layers of that manifest. I get the digest, the layers. I get basically all the layers that need to be pulled. And I would assume that after this, it's going to start pulling each layer. So let's see, there are a bunch of layers here. And then after this, I get a temporary redirect to go. Yeah, this basically requests, once I get this endpoint, there should have been a path above that we're not seeing, but the program should have requested a layer. And in this case, GHCR, which is the underlying registry, is basically sending me a redirect to their CDN, right? So as you can see, this is basically the CDN endpoint that has the blob and the HMAC signature on the URL to basically give me like a short-lived URL, so I can pull this from here. And then once this is, I got another one here, because I would assume that the client can do this in parallel, right? It can pull like multiple layers in parallel, as long as they are not like specifically dependent on each other. And once this happens, this basically just starts pulling the binary data. As you can see here, is raw data. And that's pretty much it. So it's like basically like a 4-step process. Like one.
Can you scroll up just a little bit? Basically go to the response of the blob, like to the
headers.
Yeah. So that's the interesting thing. Like the thing that it's very useful to debug what's happening when you build like a CDN. You can see a few headers there that says X cache miss, hits, and all those things. That's basically coming directly from Azure. It's like this kind of tooling for building CDN, building anything that does anything with networking. It's a lifesaver. Like it's very, very cool. Yeah. It's a type of tool that I was like, what was I doing before? Like, what was my life like before knowing about it?
Yeah, honestly, I think this is essential. Like whenever you're trying to even figure out what's wrong with a system like this, you need to have this level of understanding of which are the endpoints that you're hitting, what are the headers that you're seeing, is a sequence of requests, does it actually make sense? Are you sending the right token? At what point of the stack? Because we have so many services here, right? We have the token service, we have the registry, we have GHCR, then we have the blob storage. There's so many moving components. And it's a global system. That's the other thing. Very few of these items are actually local. Even our own registry, like the registry proxy, registry-redirect, it's a global system, which is why replacing it with something else needs to be at the same global scale. We can't just, for example, go to ECR and publish the image there. That's not going to work, right? We need a global distribution because of the volume that this registry is seeing. And if this doesn't work, a lot of Dagger workflows would stop working. And there's a lot of workflows depending on this functionality. It has to be fast and it has to be always available.
Yeah. It's actually funny, Matias. Yesterday when we were working on this, I recall that we mentioned that something was behind Varnish as well. Do you recall if it was like CloudFront or?
It was Azure. Yeah. You could see
but it's
via 1.1 Varnish, you're gonna see there.
Here. Okay.
That's the one that we were looking at. We were joking that every
Everything is
city in
varnish
the
varnished.
everywhere.
world
Everything
is
is,
just
Yeah,
varnish, and that's it.
exactly.
Like
The
that's
world
all you
runs on
get.
varnish.
The world runs on varnish. Yeah.
Pretty much.
so this
Yeah.
is coming
Yeah.
from Azure, but it's strange that it says server Windows Azure blob. Are they like wrapping up varnish in some sort of like
They
Windows
probably are.
stuff?
Yeah.
Yeah. So
With their
varnish
own.
is
Okay.
what's in front. It's similar to what CloudFront is.
Yeah.
Right? You have like some sort of
Oh, this is
HTTP
the
acceleration in
origin.
front,
Yeah.
and that is the origin exactly what serves the
Yeah.
request.
Yeah.
Man, there's
But,
so many hoops because currently it's like, so we do
Yeah.
like our machine client,
Let's
it
try.
goes to Fly, it goes to GHCR, it goes to Azure blob, and then it goes to Azure Origin, right? So it's like multiple hooks. This is Azure blob CDN.
Well, the thing is that when you go from Fly to GHCR, you already come back to the user, and from there, Fly is no longer part of the request path. So the
Oh, that's
fetching
right.
the
Yeah.
manifest, yeah,
Yeah.
Yeah.
but then every single blob that is fetched, the user is
Yeah.
just going directly to package containers. It's
Yeah,
not
this is
going
the first
through
part.
Fly or even through GHCR. It's just going directly through like that
Yes.
specific
Yeah, returns.
CDM fronted URL.
Just hit to blob
And
URL,
then we go back to the user.
client
Yeah.
basically goes back to Azure blob.
So
Yep.
actually, the client always needs to talk to GHCR. That's what's problematic. So you always need to talk to
Yeah.
GHCR because GHCR gives you those short-lived URLs, and then with those short-lived URLs, then you go to Azure Blob. So that's the one thing that we're trying to improve. We are trying to not depend as much on GHCR. First of all, we're going to reduce the load, and second of all, if GHCR is down, we won't be impacted. And I think that's even like more important.
Yeah.
So
I think what we built is the right step. Is the right step in that direction because
what did we build? Tell us about it.
yeah.
Yeah,
So
yeah.
before actually talking about what we built, let's talk.
Yes.
Let's show that it actually works, right?
Yes. Yes, that's the important part.
So I'm gonna
Does it work?
do. I'm gonna go to Dagger.io, right?
Yeah.
We're going to do an eCapture just like Marcus showed. It needs to be sudo.
And how does it
Let's
work?
see.
That's the other thing.
Okay, I don't know my password. Oh, I need to alias it and then sudo. There we go. Now I'm gonna do a Docker RMI because I've already been pulling. I haven't. Perfect. So I'm gonna do time Docker pull. Right. I'm gonna pull this particular image.
Yep.
And then stuff is going to start happening. Right. We can already see that we have the first request, which is get/v2, and that's going to basically tell us like that, hey, you are not authenticated, right? And it's going to tell us where to authenticate. And here's the first big thing that we changed. You can see that it's telling us to authenticate to registry 2025-0330. This is actually usually GHCR because that's the place where you authenticate. But there's a problem. When the Docker CLI sees this response, it's going to see that it says repository user image pull. So the Docker CLI is going to fill that in with the data that it knows. And if you see what the command is, the Docker CLI knows that we're pulling engine. So here it's going to do repository engine pull, but that doesn't exist in GHCR, right? So what we do is we put ourselves in the middle, right? There's no CDN here, like we just like send a request to here, and then in the specific request we just change it. So we see that particular request, we capture it, we change the overall response. So the next request that happens is going to go to the / token, and you can see what the Docker CLI did. It put engine instead of Dagger engine, and we need to change that before going to GHCR. So we capture this request, we change the actual like scope, and we tell it that we want Dagger/engine. Now, somewhere in all this, like something that we still need to implement is we also want to make sure that you cannot pull any random image from GHCR, right? If I do like Gerhard sysadmin, right, and I just bring in latest, we want to make sure that this doesn't work, right? Like we want to forbid this. And I actually did implement it. I forgot. I did it yesterday. My bad.
Oh wow!
But yeah, so
I did it.
This is what we want to do, right?
I
Like
forgot.
whenever
Cool.
there's an image that we don't support, based on what registry redirect does, it returns a 403. So I said, okay, I'll just return the same thing that registry redirect does. There's also another place where we were returning a 523, which is origin not reachable, but that was confusing, so I just switched it to 403. So yeah, we get the token, request, we modify the scope, and we send it to GACR. We're going to be authenticated successfully, right? So we're going to receive the response with the token that you can see here. This response, you can see that Xcache missed from CloudFront. So we are going through CloudFront. You can see X testing. This is something that I do to make sure that the lambdas are being updated, but we're going to remove them after. We don't really want that. We don't even want this header to invalidate like the entire cache or any of that. The next request is going to be head v2 engine manifest. Now, we're going to do this request again. So we're going to show that this is not being cached, even though the URL is always the same. I'm going to show how we implemented that. So yeah, we get a head to v2 engine manifest, blah, blah, blah. We get all the weird accept headers. This is the first hurdle that we had to overcome. CloudFront doesn't support accept headers sent in this format. You need to send them all like within a single accept header and then comma separated value. So we have a CloudFront function that captures that, and we'll show it in just a bit. And then we're going to see that we get a response. And in theory, this is a brand new image that I didn't pull before. Like you could see that it just pulled it from scratch. And we get a miss from CloudFront, right? We also get some information on the edge location that I'm going at, ECE. This is Buenos Aires. So yeah, we start getting like all this information. We get the full response. We get all the things that we need to get. So here's a manifest, right? And then we continue sending all those requests. We get all the layers. Like it's basically the entire thing. It goes on. Yeah.
So what happens if you do the request again?
So what
gets cached? What doesn't get cached? That's very interesting.
So we get the v2, same thing that we did before. We can see the response. We can see that it's error from CloudFront. This is something that CloudFront automatically does. If you get a 401, it's not going to cache it. You don't even need to specify that you don't want to cache. Never going to happen. So we just modify it, and that's it. We get the request, we get the token. You can see miss from CloudFront again, even though we already did before, but this has no caching configured, which is what we want. Tokens get refreshed. We get the request to v2 engine manifest with all the accept headers. And here we get the response, and we see that it's a hit from CloudFront. This is the one that actually like gives you the initial, the initial manifest that you want to get. I don't know why we don't see like on I think the output is being like, confusing, but we should see somewhere, the actual JSON that we were looking at before. I imagine it's going to show up somewhere. But
yeah, sometimes it's like basically,
So yeah, you can see that there's a bunch of requests that are being logged one by one, and the responses are not there. Here you can already see that we're fetching like the manifest for one specific like what do we call it? One specific like SHA, and we haven't yet seen a response. Here we can see, for example, so this is a response for the initial request that we made. So this response here is the one from this one, right? And we can see that hit from CloudFront. And we see the JSON. This response should be manifest. So this is another one. This is a request. This is a response. And it's, again, a hit from CloudFront. And this is actually like the full list of layers. So this is the one that we were looking at a little bit further up, which is nice. I'm going to continue scrolling. And here we have a request to one of the blobs, right? I think we're going to get the response, which is going to be like kind of messy because it includes all the binary. Let's see if we can find. We should be able to find, because I sent a screenshot of this.
Do we know if that's cached? Do we know if this response is cached?
It should, and that's where I'm looking for. Yeah.
Okay.
Because I already sent actually these to Marcos, and the response is confusing because you get all the Azure headers and all the CloudFront headers, so you get to see like pretty much everything. And here we are. So this, you can see that this is application octet stream. So this is a response from some of all the blobs that we're downloading, right? Like it's I think the output is going to get confusing, but we can see that this one was a hit from CloudFront. And we can see that it's application octet stream, content length, so it makes sense. Like this is a blob. So we effectively cached a blob directly from the CDN, right? And it's mixed in with all the binary data. If we continue scrolling down, we should find. Oh no, because I stopped it. So that's all.
Yeah, that's okay. That's fine. This is really good. So just just to double check that I understood this correctly, we are still depending on GHCR.
We are still
The
depending on
only
GHCR.
dependency is the token, right? So on every request, we need to get the token before we continue with a subsequent request, regardless whether those are cached or they're not cached.
Yes.
I see.
Yes, but it wouldn't be hard to stop depending from it.
Okay.
Because if you think about it, if we're able to fully cache everything, right, and make sure that we have the data, then what's the token for, right? In fact, initially, I had like caching configured for the /token path, so the token was being cached, right? And I used it for hours, and that token doesn't last for hours. And I was able to pull the images because I was going through the CDN. So while I was making, while the Docker CLI was making the token request, and we were actually serving that request, because the token was not really relevant for CloudFront, and because the data was being served from CloudFront, I was never going to GHCR.
I think this is really cool. This is really, really cool. And I think it will be important for us to remove that last dependency so that if GHCR is down, Docker pulls will continue working, right? Because if you think about it, the only reason why Docker pull would stop working is because we need the token. I mean, we are making, no, we don't need the token. We're making the request for the token, even though the token is not being used since things should be cached. The other thing that I think we'll want to do is set up a shield origin. The reason why I want a shield origin is because every single POP will need to go to GHCR to fulfill the request. If we have a shield origin, it means the request will go to that one place or that one CloudFront location, which if that has it cached, then every other edge location can fulfill the request just by going to CloudFront. But that's like, I suppose, like the second improvement. But the first one is the token one, so that we don't depend on it. And if the edge location has it, has all the layers, GHCR can be down, everything will continue working as it should. Really, really good stuff. How does it compare in terms of speed? Last thing, and then we wrap it up. So how does it compare if you do a time?
I think it's going to depend on
for you.
On your
I mean, for you, if you were to
for
if you
me
were to pull it down,
it's usually around the same performance between the two. So I'm gonna do time docker pull. This is gonna be 0.18.14. Sorry,
that's the last release.
So let's pull that. This is the one that we already pulled, so this already should be cached. In fact, it's the one that I've been using to test. It's usually around like 10 seconds, I think, for me. Sometimes it might go a little bit higher. Now that I'm also downloading stuff, like I have the video being downloaded on Video Ninja. Yeah, this is not usually what I see. Like I usually see around 10 to 12 seconds. Now let's see. Docker pull registry.dagger.io engine 014.
You need to remove it first, right?
I already removed this one.
Oh, you did? Okay.
Oh, I didn't. Oh, because I need to remove the other one as well. So I need to remove that one, and I need to remove this one as well. There we go. And now I do a Docker pull. There we go. So there's unloading. Usually I was like around the 10 to 13 second mark for Docker pulls, both on GHCR as well as on CloudFront. Like for me, performance was roughly the same, maybe slightly faster, but
I mean, seems to be going
maybe like
seems to be going a bit slower than the previous one, right?
Thing, right? GHCR might like drop the cache for your images depending on like the volume that it's getting, right? So that's why it can go up or down. We can
34 seconds.
I can remove it, right? Let's
try again,
and then let's do Docker pull, right? I would imagine usually this one's gonna go faster.
Like when a cold cache, and the cache is primed, so this will make a difference. Like for sure,
GHCR needs to handle cache for like thousands of images, we just do the one.
I think that's exactly where this gives us so much more control, right? We get to keep things in cache
expectable performance.
Exactly, for as long as possible, but it's still slower. So it's still 24 versus 16.
This is not what I've been seeing before, though, so I'm not sure what's going on today.
The other thing is the variability, right? Like, just depends on the load of the service and what else is using it. Networking, just so many considerations there. But I'm very curious to see, let's do a third one. So we had 36, 24. Let's see what a third one will do.
And then let's not only because of that, take into account that for each blob that you want to pull, you have to make a request to fly Fly needs to go to GHCR. You need to get the
blobs go directly from the user to
Yep.
to GHCR. We don't capture blobs. We only capture manifests.
No, wait. That's not what I was saying. Like for a standard flow, the client needs to get the 307 that GHCI returns. So you go to the CDN that they have, right? That request to get the 307 for each of the blobs, because each of the blobs goes with a signed URL. You need to make one of those requests per blob. And that request is going to take time because it's like more latency going to Fly than to go into CloudFront.
That is correct, yeah. But I want to make sure Fly is not in the middle in that case.
To get the blob, don't you go to Fly?
No, to get the manifest, you go to Fly. And then from there, you always go to GHCR. You do go to GHCR, you do get a 307, and you do go to package containers. But you don't go to Fly for that path. Yeah.
It's just like the initial one to get a manifest and to get...
and then that's it. Yeah.
That's it, yeah.
Yeah. Which was part of the problem, right? Because we don't have any visibility on the blobs themselves, which, not a huge deal. So we did get 28, right? Which was
28.
24, we
28.
got 26, 24, sorry. So I'm going to pull this one again, which we only pulled once. And we already removed this one. Yeah. So let's pull it again. And then let's see.
After this, what happens next?
Man, that's way faster. You can see it visually, actually. Yeah. Way faster, actually.
Yeah. I guess this confirms, the variability that you get when you use a shared service, because this is not the experience that I was getting the other day. I was getting the same performance from the two, like around 10 to like 13 seconds from both GHCR as well as this one, CloudFront. So yeah, I guess it's some days it's going to be better, some days it's going to be the same. We are going to give more consistent performance because we serve the one image. So yeah.
Yeah, very nice.
To configure a CloudFront fronted registry, we couldn't really find a lot of content that wanted to do this. I guess, you try to use GHCR as much as you can because doing this costs money. So we went rogue, even without AI. Crazy to think that we did this without AI. I'm lying, of course. But yeah. So I'm not going to get too much into this behavior in particular. We're just going to look into this one, and we'll talk about some optimizations we could do. So CloudFront, you get like what you get when you get to create like a distribution. You have origins. Origins are like the destination that you're going to. You have behaviors, and then behaviors are the things that actually tell you how you want to cache, what kind of lambdas you want to execute, if any. Like gives you that kind of behavior, right? Self-explanatory. So origins, we have two, which is important. We need to go to GHCR, but we also go to package containers, and we'll explain why it's an origin. And this is an optimization that's also like helpful in making the request a little bit more performant. So I go to the behaviors. I open up default, right? I'm going to edit it. I want to start looking at what this does. So the main origin that this behavior fronts is like GHCR, right? That's the default one that we're usually going to. We have a caching optimized policy, which is one of the default cache policies that CloudFront provides. It just supports gzip, it supports broadly, and it caches everything that it can based on headers. We have an origin request policy, which is send all the headers that we are receiving except the host header. This is important because the host header is going to be registry 2025-0330.dagger.io, and we're going to GHCR.io, so we don't want that to be the header. We don't do any response headers policy because we don't need to. And then the fancy thing is that we use this function associations feature that basically allows you to execute arbitrary code that you author, whether that's a Lambda or a CloudFront function, and we'll talk about the difference in a bit, on different parts of the request lifecycle. So the way that this works is viewer is us, the client. So the client initializes a request, and if you want to modify what CloudFront is going to see from the user, then you specify a CloudFront function for the viewer request. And here you can mangle with the headers or not much, just the headers and some other stuff on the request. But you can basically change a little bit the data that the client sent before that reaches the CloudFront CDN. After that, we get all the way to origin request. This is a function that gets executed right before sending a request to the origin itself. Now, this request in particular, it's usually like it allows you to do a lot more stuff. Like you can actually even make other network calls yourself. Like you can actually do like some powerful things. This is executing a Lambda, not a CloudFront functions, and Lambdas are a lot more powerful. Once you get a response from the origin, this Lambda is going to be executed if you have anyone specified. And then once that is executed, this one is going to be executed, which is the viewer response. So what do we want to send back to the viewer? You could do everything on origin response. You could mangle origin's response just enough so that the viewer sees like what you want to see. But viewer response, origin response, it makes it clear like what you do where, right? So we get the viewer request, we get CloudFront, we get the origin request, the response, and then the viewer. This is perfect. So you can see here that we configured basically every single one. This is something that you need to be mindful of because this costs money. We can open up the pricing page, but given that AWS makes it hard to see prices, we're going to take a while. So you need to trust us that CloudFront functions are way cheaper than Lambda functions. So if you can get by
10x?
It was 6x.
Six times. 6 times. Yeah.
Okay.
So if you can get by just modifying viewer request and response without touching lambdas, that's going to be 6 times cheaper. If you can get by without doing any of this, that's going to be like much
the cheapest,
cheaper, right?
Of course. Yeah. Sure. Do we remember how much we pay for like per million requests? I know there was like some number of cents or something like that.
I think it was like 1 cent, like 0.1, because the other one was like 0.6 or something like that. But I'm not sure. Yeah, per million.
0.1 cents per million. Yeah, I remember something similar.
Yeah,
it was
$0.1.
$0.1.
Yeah.
Are you referring for a Lambda, Gerhard?
For CloudFront. Yeah, and then the other one was 6 times more expensive. Yep. Yeah,
I remember that as well. So 0.6 per 1 million Lambda functions.
Yeah,
0.6 per 1 billion notifications.
Yes,
and 0.1. So like 10 cents for 1 million CloudFront invocations.
Yeah,
and this will be a request, and we handle about 3 million per day.
Yeah, so we configure each one. Now, each of these are going to do different things. They basically capture the request that we send to JCR and do some changes so that the registry actually works, some magic. Yeah. The thing is that here we have the most expensive setup that you could have because we are filling in
all of them,
every single stage of the request. And we're doing this for every single path. The thing is that we already saw that not all paths are the same, right? So here you can see that we have a behavior, and the behavior has a path pattern of everything. When I was showing it before, I already teased that we have like a separate behavior for token, right? And you can see that it has caching disabled, right? So the way that we could optimize this further, next time when we start looking into the actual code, basically is okay. For the different path that a Docker pull needs, right? For the blobs, the manifest, and all these things, what do we actually need to execute in order to fulfill that request, right? And we're gonna see, like I can tease like ever so slightly, like here, we're gonna see that for different paths, we are gonna need different kind of like stages, right? For example, for token, we only need viewer request with no caching. For V2, we only need viewer request and origin response with no caching, but only because it's a 401. And then for V2, like wildcard, we need a viewer request. Maybe we might be able to get rid of it, and an origin request, and that's it, right? This is already going to be a cheaper setup because it means that, for example, for fetching blobs, which is going to be the bulk of the volume that we serve, we're only going to be executing one origin request without having to do origin response. So it's already half the price, right? And it gets even cheaper because we don't have any viewer response. We only have a viewer request, and we might be able to get rid of it. We're not going to be able to get rid of the origin request, but we might be able to get rid of the viewer one. There's some interesting optimizations that we can do cost-wise. Performance-wise, it's pretty much what we have. We're not going to get any better than this, but
It's actually almost 100% faster than pulling from GHCR directly, according to what we saw minutes ago. So it's quite
I
fast, right?
think it's gonna come and go, but yeah,
how's that for a blog post? Achieving 100% performance gain over GHCR using CloudFront.
Yeah.
That's Amazon marketing.
It's 1,000 times more expensive because GHCR was free. yeah.
Exactly.
Okay. Yeah. Stay tuned for part 2 or subscribe for part 2.
Yeah, for sure.
All right.